So, good morning. It's 9 o'clock here in Denmark, and today I'm going to give you this webinar here on operational modal analysis. We're going to do a little testing on a plate using operational modal analysis. My name is Paul Andersen, and I represent our company, Structural Vibration Solutions. So the outline of this talk today is I've split into these 4 sections here. First of all, I'd like to give you an introduction to operational modal analysis. Then I'm going to show you how you can actually set up a simple project to do a test on a structure. We are going to use some multi-setup testing in this case here. And then as a part of this demonstration, I will focus on a special topic today that is frequency domain singular value analysis that we are doing both when we are testing the structure and also we are using it extensively in the analysis later on in the software. So we're going to talk a little bit more in detail about what you can actually get out of these this kind of analysis here during your test, but also afterwards. And then finally, there will be some conclusions. So this is the program for, I guess, the next hour or so that we'll go through these things here. The first thing is, of course, just to make it very simple, a simple introduction to the concepts of modal analysis and operational modal analysis. Operational modal analysis is only one of different methods that you can use in order to extract modal parameters. We are splitting it into 2 different categories. Experimental modal analysis, where you are using measured input, and then operational modal analysis, where you're using whatever input is available, and you're not measuring anything of that sort. But in both cases, we are trying to hunt the same parameters, the modal parameters here. So you can imagine we have a structure here that is vibrating in due to some excitation that has caused this vibration pattern to happen. And we are here in physical domain. So when you look at the structure, it looks very complicated the way it is vibrating. What we then do in modal analysis is we simply try to split it up into more, say, fundamental building blocks. We call these the modal parameters. The most obvious one to look at is the mode shape. So the mode shape of the first mode is a very simple one that is, in this case, only a bending back and forth like this. Along with this mode shape here, there will also be a natural frequency, and there will also be a damping ratio. So there are these 3 parameters that are describing a single mode of vibration, and there will be many of these. There will be a whole bunch of them that has been excited due to the excitation that we have supplied to this structure here. So adding these together will then ultimately give us, you could say, the response that we have been able to measure out here. So modal analysis is simply a nice, convenient way of splitting this complicated vibration pattern into some more fundamental building blocks. The good thing is, when we are doing this kind of analysis here, operational modal analysis, we can actually do another kind of analysis also, because when we are doing operational modal analysis, we are working here in this domain here. This is the modal domain over here on this side of the equation. But you can also actually study the overall vibration pattern of the structure. You can do that in the physical domain over here. And this is called operating deflection shapes analysis. And the measurements that you have to do for operational modal analysis matches the ones that you have to do for operating deflection shapes. So there is actually a lot of things you can get out of the same data in this way here. So that's one of the benefits also of this. If we step a little bit back and then we look at the classical way of doing things, then we are in the field of experimental modal analysis or classical modal analysis. The idea of classical modal analysis is that we try to test some structure that we have to assume is a linear structure and a time invariant structure. We will test that with some known excitation. This known excitation can, for example, be an impact hammer like this one here. So we are hitting the structure in different positions. This hammer here, we have a force transducer sitting here that actually measure then the force that we are supplying. This is one way of doing or impacting or exciting a structure with a known excitation. Besides that, we then have to mount some sensors, typically accelerometers, on the structure that can actually measure then the response in one or more points during this test here. Having response and excitation measured, we can then take this to frequency domain, and then we have a response spectrum. We can divide that with the spectrum of the force. Then we get a nice clean function we call frequency response function that is only dependent upon the actual structural system here. And that one allows us then to extract the modes very conveniently. The only thing that is a problem here is that we actually have to be able to measure all the excitation and of course response in some nodes that has been supplied. All the excitation that has been supplied has to be measured, which means that there are limits to what fields or applications where you can actually use this kind of technology here. Everything when it comes to testing civil engineering structures, testing machinery that is running, testing ships, other things that is out in Mother Nature, we have to turn to something else because we cannot measure the excitation forces in these cases, and therefore this type of analysis doesn't really work so good. That's why we have operational modal analysis then. This is just an extension, you could say. It's another kind of domain we switch to now because we are still trying to get parameters from the structural system. We have the same assumption still, linearity and time invariance of the system. But now we have unknown excitation forces. Something is exciting the structure, but we cannot measure this excitation here. We can only measure the response that the structure is giving to this excitation here. So we have to do some assumptions in this case here when it comes to operational modal analysis. And one of the major assumptions we are going to put here is that the excitation basically comes from a so-called Gaussian white noise. So we actually assume that the excitation of this system here is a Gaussian white noise. And what is that? Gaussian white noise is simply a kind of a force spectrum that is completely flat. It has the same energy at all frequencies, and it's exciting in multiple points. So we call it multiple input, multiple output in this case here. I'll come back to later on why we would like to have multiple input. It's very easy to see when we don't have it, I would say, and by using these singular value analysis I'm going to talk about. But it's a very common assumption, and it's one that we use for all our methods that we have, that the excitation should be in some way assumed to be related to a Gaussian white noise, something broadbanded, something that excites many, many frequencies, not just a kind of a sinusoidal excitation that only excites a single frequency. That doesn't work here. We have to have something that excites a band of frequencies. Gaussian white noise is completely flat, but normally when we study how excitation is distributed, let's say on if you go to the ocean or you go to the wind, and you check out how the distribution of how this is looking, then you will see that there are some parts, some frequencies that has more energy than others in these type of spectrums of input. So we would like actually to be able to fit this into this this system here, that we can actually have a force spectrum that is not completely flat, but has some kind of peaks somewhere, some smooth peaks. We do that by inserting what we call an excitation filter here. This one here is a filter that shapes the completely flat Gaussian white noise into whatever excitation forces we are actually applying to the structure here. This is the kind of mathematical framework that we set up. It's not like we are going to model the excitation or anything before we can do operational modal analysis. So you should imagine that we are trying to fit everything inside this little box here. Everything, both the structural system, and if there is something related to some excitation that is not completely flat, that in some way will also appear in our model. And the art is, of course, that we extract the part that relates to the structural system in the end. But you should imagine that the only thing we have up front is response measurements from some points. And based on that, and based on this kind of mathematical framework here, we are trying now to extract the most of this system here. There are different ways we can do it. It really depends a lot about, you could say, especially how much money that you want to invest in hardware. If you say have enormous amount of money, so you can just buy whatever number of channels that you want for the data acquisition system and sensors and so on, you can simply mount the sensors in all the points and directions where you would like to know the mode shapes of your structure. And then you make a single measurement. We call this a single test setup. But in many, many cases, you will have to accept that your budget is not that big as the number of degrees of freedom that you would like to find mode shapes in. So you have to be a little bit more smart with the usage of sensors. And we do that when we use so-called multi-test setup testing. And the way it's working is now we have a car here that is in operation, as we can see. We have 3 sensors here, plus we have 2 here. That's 5 sensors, you could say, we have available for this test here. So we put 2 of the sensors in some well-positioned locations where we believe that there are good, you could say, amplitudes from the different modes that we would like to extract in this analysis here. If we are not sure about where to put them, it's better to put a little bit more reference accelerometers, sensors, in different locations because the probability that you will find spots where at least one spot where the modes have some good amplitudes is of course higher the more reference sensors you are using. You can of course use different kinds of tools prior to the actual testing here. You can study a fine element, for example, and you can look at how the mode shapes are behaving of the structure from a fine element model. That can also help you to plan where to put these reference sensors here. But otherwise, besides these reference sensors here that we will keep mounted in the same position here, we will then put the remaining sensors we have in some points and then start doing a test. So we will be measuring for a while the structure is running and we have some response coming out. And then after a while, we will then stop the recording and we will move these 3 sensors to new positions here. We will keep the ones we have over here, the reference ones, they stay there at the same place. But we have the other 3 here now moved to another part of the structure where we also would like to know the mode shape. And then we restart the recording of the ones. So you can imagine we do this over and over again, as many times as needed in order to be able to cover all the points on the structure here. This is called multi-test setup testing. This is the way we are going to use here today. I have a simple structure. It's just a plate. I have it lying here on the table here. I will show it in a minute. But the way it looks here is simply that we have 16 points here on this plate here that we would like to know the mode shape in. We only have 10 accelerometers available. So what I have decided to do here is I want to put 2 sensors here as my reference sensors. And then I have 8 remaining sensors here. I can put them up here as a first setup, make a test. Then I will move all these 8 sensors down here to these locations down here afterwards. And then repeat the testing and then getting the second setup in this way here. This is just to illustrate how you can do it. If it's a steel plate like I have, or it's a huge cable stay bridge, it doesn't really matter. It's exactly the same way to do things. It's just a matter of what equipment you are choosing and how long time you have to measure. So what I'm using here now is simply a simple system here. It's a National Instrument system we are using today. It's a nice little thing where you have a kind of chassis, a CDAC, where you can stuff in up to 4 modules that each has 4 channels. So it's easy to go from 4 channels to 16 channels in this case. We're using 3 modules here, allowing us to get to 12 channels. And we're using 10 of those where we are then using these B&K sensors here. One thing that is really nice with these is that they are touch sensors. That means that they have calibration information built in. So that when we start the acquisition, we are actually getting all this information directly from the sensors, and we don't have to set up anything regarding calibration information otherwise. So that's pretty nice. But let's see here. I will try to see if I can move my screen here a little bit and hopefully show you something here. If I move down here a little bit, also let's try that. Then hopefully you can see it now. The plate here. Here we have the measurement system here with the 3 slots inside here, the 3 modules we're using, and with the 10 channels attached. So this is the plate we are going to model here. And let's try and jump into to ARTeMIS now, and then get started with setting up this project here. So I will switch now to ARTeMIS. We are now using the Pro version here, but what I'm going to show you here, the setup part here, is available in all the different versions we have. It's just a matter of which estimation methods we have available that is different from the different methods in this case here. But the first part here is the same for all our different versions. We start here by creating a new project. I do that by right-clicking here, then I get different options. I choose to use a blank OMA project here. I use something we call internal storage. That gives me a single project file in the end that has everything inside. So it has the geometry, it has the information about where the sensors are located, how many we're using, and how many setups, and also, of course, results and so on. Everything is kept inside the same project. This is a really convenient way because then you don't have to manage a lot of files. In some other cases, we have to do other things like external storage. That's when we are doing monitoring of a structure over a long time. Then we cannot keep everything in a single project. We have to in some way divide it into multiple files. But here we are going to use internal storage here and use blank project. So when we started up here, as you can see, it looks really blank, not much to see. The first thing I have to do is I have to go to the task that allows me to make a geometry that matches this structure here. Right now, as you can see, I'm in a task we call a setup task here, and then it's manage measurements. If I go here to these controls here, I can see that I'm here at this second task here. I will go to the first setup task here and then select this one here. Here you can see a simple way to make drawings. You can add some nodes and lines and surfaces, and you can make all kinds of objects in a hierarchy so that you can make all kinds of sophisticated objects or geometry here. But there is another shortcut we will use here, that is simply to insert a predefined object. We'll use a filled rectangle in this case here. So now I have this little drawing pencil here. This one I can now start putting to one of the corners of the structure that I'm going to draw. Then I keep the left button down on my mouse, and then I move to the other corner, and then I release it like this. Now I have my plate. The only problem here is that I only have 4 corner points. I need a little bit more because I have 16 points, plus I have the 2 reference points also. So I need to subdivide this plate here a little bit. I do that by clicking here to activate the properties. Now I can now choose a little more dividers here. So I use 3 in X and Y like this. And now you can see suddenly we have much more nodes in this structure here, the number that we need. The only thing that we are missing right now is actually these 2 nodes that we need for the reference sensors. They can now be manually added by clicking this little button up here. And again, I get my little tool here. Now it shows you a dot or node. And I can put the first one here. And then I can go down here to this point here and then add one here also. These can of course be fine-tuned in X, Y, Z and so on if we need it, but let's not spend time on that now. That's it. That's the geometry we are going to work with. We have 18 nodes here spread out on this structure here. Okay, so now we go to the next section. This is where we have to now define how we are going to do the testing. We are going to insert 2 setups. Under each setup, there is going to be 10 channels. We are going to then tell where the different channels are located under each of these setups here. And that's the plan for now. So I'll go here to the top level here. I will insert first a test setup. Then I will insert 10 channels like this. And now I can drag out the first channel to my first reference here. Second channel will go to the second reference like this. And then we continue with the one that are going to move from one setup to another one. And these are the remaining ones we have here. Like this. And we are nearly there now. So this is my first setup. It looks like this. And now I need to make a second one also. And I can do that by going here and then I can right click. Then I get a replication tool here that allows me to make a copy of this test setup here and reuse some of it at least. You can imagine if you have many setups, it's a convenient thing to do. Otherwise, in this case here, you could actually do it manually from scratch. But just to show this tool here that allows you to select how many new setups you would like to make. And then here you can also specify that the first 2 of these sensors here, that will be my references. That means that when we now replicate, they are already assigned to these positions here in the new setups. So we don't have to spend time on that later on. Then I click replicate here. And now I get my second setup here below the first one. And you can see already that we have the reference sensors. They are green here. They are already mounted on the 2 positions. So we are simply going to use our time on the last 8 channels here. And I'm dragging these out here like this. Like this. Very good. Then we are finished now with setting up for the test. We have 2 setups. You can see now we have 2 blue arrows showing up here. The blue color indicates that this is the reference sensors that are kept fixed there during all the test setups we have. You can see the greens ones we have here. These are the moving sensors. These are the ones that currently are chosen because we have selected setup number 2 here. There are some gray sensors here also. They are just indicating where there are also sensors assigned to in other setups. So that's quite convenient if you have a really complicated structure that you can remember, okay, I went to this point here. So this is I have already this one here attached, so it must be the next one and so on. So it's good to have this little indication here also where you have done something before. That's it. We don't need to do more here. We can now go to the part that relates to the real-time testing we can do inside ARTeMIS. We have different options, as you can see here right now. Currently, we have 4 different types of hardware we support. The one that I have here in front of me is a National Instrument device. So we will choose that one. And now we are communicating with the hardware, figure out what it is, how many channels we have and what sensors there are there and so on. And you can see, because we are using these touch sensors, they already actually showing up in green here. They are all being attached automatically to the project here, simply because we already know everything about them. Otherwise, if it was sensors without touch information, there will be a red light here, and you will have then to select from the database we have you can set up. You will have then to select which one of the sensors it is that it in fact has on channel 1 and channel 2 and so on. But here we know it because we simply ask the sensor itself. So I simply click OK here, and now we start up the acquisition part here. And after a while, something should appear. And it looks like this. This is the appearance of the data acquisition when we are talking about operational mode analysis. There is another kind of layout if it's for classical mode analysis and impact testing and so on. But for operational mode analysis, it looks like this. We have up here, we have a table. We call this data acquisition setup. This gives us an overview about the different sensors and how they are mounted to the channels we have in our project. Currently, they are not mounted. You can see the channel name is this name here is coming from the device itself. But here there should be a channel name corresponding to one of the channels that we have actually inserted here. So we are missing this part here. So we need to assign that the first hardware channel here is pointing to some channel inside the project. And it's fairly easy if it's the same way that we have defined, you say, the channels in the project as the way that it's actually made in the hardware part. So the way we have placed our sensors on the structure is exactly the same way as we did the assignment inside the project. If that's the case, where there is this one-to-one relation, we can do something we call auto-assign. So I simply click this button here and say yes. And now there is a link between the first hardware channel and the first, you could say, software or project channel, in this case here. And for the second hardware channel, we have then the second channel, this first setup. And you can see here, this is the first setup we are working on here. We will be measuring here first, and then once we are finished with that, we will move the sensors to the other position. We will then select second setup here and then repeat the testing. But otherwise, all the settings will be the same. The next thing we can do is we have to configure what we should do with the data acquisition system. So when we click this configuration button here, we get this little dialog here. This one here then shows a list of all the available sampling rates, sampling frequencies that we have, or the instrument has. And we can then select one number of hertz that is convenient for us. And I think I like to go to 5,100 hertz here. That will give me then modes up to around 2,500. That is the Nyquist frequency then. So that's a nice good range of modes for this particular test here. The next thing we can do is we then have to specify how we like to do the recording. There is different options. There is a manual one. That means that you start and you stop manually. So you choose how long time the recording should be, and you choose when to stop. But you can also choose an interval recording here. In this case, you have to go to this options here. And here you have to specify the length in seconds of your measurement. We will put 60 seconds in this case here. There is another option here, because we can actually make it start automatically. So that means when excitation starts appearing, then the software will automatically start recording. We can do that by enabling a triggered recording here, like this. That's it. We press OK now, and we press OK here also, then we are basically ready to do the recording. But we have to choose up here, one of these channels has to be the channel that we use for the triggering, for the start, the automatic start of the recording. We just choose the first one in this case. Here we use an absolute trigger. That means that when we have a threshold of, in this case here, 0.25 G, when the vibration in some way exceeds this in an absolute way, then we start the recording. So this is the way to do this. We can also add some diagrams here that allows us to see the data coming in real time. And then there is another thing here. This is the one I'm going to talk a little bit more about. But let's start by clicking some channels here. So we select some of these channels we would like. We can choose all of them, but or some of them. We can do these first 8 of these, perhaps. These are the channels that we are going to use for this singular value decomposition in frequency domain. And this is something that will appear over here. We can try start putting on idle, and then you can see a little bit of what's going to happen here. If I now take my pen here and then I start doing something like this, you can actually see this diagram here appearing like this. This is a diagram that is being updated continuously. So you can see a lot of things here. So this is the kind of diagram that I'm now going to talk a little bit about. Let's try and stop this one here and then go back to the presentation. Where are we? We have to go there. We go to the next slide here, like this. We're going to talk about now the frequency domain singular value analysis, or singular value decomposition of spectral densities, as it's more, I would say, correctly to say. What we do here is actually we are trying to use a method that allows us to see everything from all the sensors in a single diagram. Normally, you will see in data acquisition systems, you will be able on the fly to see spectral densities. If you have 3 channels, for example, you will have autospectral densities. There will be 3 of those. And then there will also be all kinds of cross spectral densities. This is between 1 and 2, and this is between 1 and 3 up here. And here is between 2 and 1, and so on. So there's a huge amount of spectral densities to look at. There is actually, you could say, the square of the number of channels. So that means that if you have 3 channels, okay, you have 9 spectral density diagrams to monitor. But let's say you have 100, then you have 10,000 instead. So it grows dramatically because of this. And the good thing is that you can actually make a diagram, a single diagram that will show everything in all these other diagrams that you basically would have to monitor to see all the dynamics of your system. So that's the singular value decomposition that gives us this ability. You can imagine, you can see the stipple line here in all the diagrams. So let's imagine that we are picking out, we're choosing this value here in all of these diagrams here that is at the stipple line here. We stuff them in, these 9 values, into this matrix here. This is now our spectral density matrix for this particular frequency here. And then what we do is we do this singular value decomposition. This is, we split this matrix here into 3 matrices. There is a left singular vector matrix. Today we are not going to care about that so much. There is also a right singular vector matrix. We are not going to care too much about that either. But we are going to care about this one here. This is the matrix of singular values. This is a diagonal matrix. You can see it down here. It only has 3 values that are non-zero. And these are the values that are of interest, of course. If you put those at the same frequency as where you grabbed the ones over here, now we can stuff them in here in another diagram here. So we take the first singular value, we put that up here. the second one we put below here, and then we take the third one and we put it down there. And then we repeat this for all the frequencies, from the very first one at DC, 0 Hertz, all the way up to Nyquist frequency. If we do that, then we generate this nice diagram here, a single diagram with 3 lines only, that shows us everything for a 3-channel system. This is the beauty of the singular value decomposition. So we are now, we would say, linearizing the problem. Instead of having the power of the square of the number of channels to monitor in the spectral density domain, we are now back at actually only looking at the same number of singular value lines as we have measurement channels. So that's a really nice, you could say, simplification of the thing, and still you see everything in a single diagram. Let's try and see. If we go a little bit further here, there are different things we can see in this diagram. That's why I like to emphasize a little bit about this today. Because the first thing you can do is you can take a look at this structure here. This one is a rectangular plate. That means that it has some bending this way here and some bending this way here, but it will not happen at the same frequency normally because of the difference in the two sizes. So when you look at data from this plate here in singular values, it looks like this. You have a bunch of nice looking peaks here all the way here. Then there is something here that is a little bit special, but then there are other nice standalone peaks here. We call these peaks here for, say, the peaks of well-separated modes. That means that there is a nice distance to all the other modes in this structure here. It also means that there is only one of these lines popping up. You can see there is only the blue line here popping up. There is nothing really happening in all the other lines down here. This is because at this frequency here, there is only one mode that basically dominates the whole thing. The whole frequency range around this resonance point here is dominated by a single mode. That's indicated by a single peak popping up here, showing that the rank of this matrix here is 1, basically. Then we can see as we proceed down to the, you say, the middle point between two modes, suddenly you have 2 of these singular values popping up. At this point here, the 2 modes, they have equal strength. So they are just as energetic, both of them, and they are now fighting who is going to be the one that wins. If I go this way here, the second one will win, because now the energy of this one will increase, and there's nothing left from the second one. This is the remnants of the first mode. Is the remnants of that one is the one you can see down here. So there is nearly no energy left there, but the second mode here is really strong now. So this way you can actually study, you say, the whole range of modes all the way through and see who is actually dominating here. We can do that because we have all these additional singular values down here to help us. We can see that we have one mode coming up here and going down here, going to the red one now, and then continuing down here to the green one here all the way. So we can visualize, because we have all these lines here, we can visualize the way that this mode is actually behaving through the frequency range. This can, of course, only happen if we have the lines. And the lines here only appear when we have a multiple excitation points that I'll come back to. Let's just continue with another observation here. This is this part here. Here you can see that there are, it looks like 2 peaks up here, but you can be a little bit unsure if you only have the, you could say, this blue line to look at, if this is 1 or 2 modes. We can zoom in a little bit over here. This is what I've done here. What you can see now, because we have the additional singular value lines, is that the second one is actually popping up here, and it's popping up to the middle point between the 2 peaks. So this one here is pointing to the middle between the 2 peaks we have up here. This is indicating, since we have 2 lines popping up now in this range here around these peaks here, it indicates that we have 2 closely spaced modes here. And we have the second helper here, the red one here, that helps us indicating that. Otherwise, we could have been a little in doubt if we only had a single blue line to look at. So in a case like this, even though we have this rectangular plate here, we can actually observe closely spaced modes also. That means that the distance between them in frequency is not that big. This is the case here. Then there is another type of structure. You could imagine if this one was a completely symmetric structure instead, then suddenly it bends this way here, and then this way here, in exactly the same way, or the same frequency. In that case, the singular value decomposition changes a little bit the way it looks. You can see here there are some well-separated modes in this case here. This is just another symmetric plate I have been testing. At this point here, suddenly we have two of these singular values popping up to the same frequency point here. So they have resonance at the same point, and there are two of those. That means that we have two modes having resonance at exactly the same frequency. This also repeats itself over here. Now you can again see two pointing up to this point here. And then there is an additional third one here that is coming from the green one down here and then all the way up here and then down this way here. So this way you can actually, by visualizing it, combining the different lines, you can actually see the different modes. This is also why this is called a mode indicator function. This is the primary use, you could say, of the singular value decomposition, but there is also other things that you can actually see. And that is also important while you're doing the testing. This is something that you would like to see when you do the analysis in the end, when you have done the measurements, because this is where you then need to know, do we have closed modes or not, or what do we actually have in your data. But during the actual measurement, there is something that is also very important to see from this diagram here. And we can start here by looking at what happens if we have a poor signal to noise ratio. In a case like that, you will actually see that instead of having a diagram that looks something like this, if you now have a lot of noise and the modes are not really excited very good, then you end up having something looking like this. And you can actually see it's like the flat part here is raising up here towards the peaks, whereas the flat part down here is way below all the peaks. The flat part here, we call this the noise floor. This is, you would say, basically the lower limit to where you can find something of meaning that you can extract when you're doing the modal analysis. There might be something below the noise floor, but if it's below the noise floor, it really doesn't look good when you're trying to extract some of the information. Mode shapes look terrible and so on, and it's very, very uncertain. So you should aim for to have all your modes above the noise floor. And this is the case over here where the noise floor is down here at the first really flat one, the green one we have here. Whereas if we go here to this one here, we can discuss, is it this red one here or is it this red one here? That is the noise floor. But at least we can see that no matter which one we choose, there is something below here showing up as peaks. But these peaks, they have drowned because they are below the noise floor. So that means that if we try to extract these, the mode shapes, they will just be, they will look like noise. It will be really, really messy to look at when you animate it. And it has really no sense in trying to use it in any kind of report. So you have to make sure that if you see this kind of behavior here, when you start the test, you have to go and check your instrumentation, or you have to go and supply some more excitation. We can try actually to see this, how this looks over here. Because if I now start again here, and we simply wait for the diagram here to update, you can actually in some way see this already here. You can see how the noise floor is actually here, all the way up here. And it's like all the modes are in some way truncated to this noise floor here. There is really nothing happening below. But if I start adding some excitation, then we will see that we are now raising all these modes, they will pop up over the noise floor and of course give a better level of response. Well, at least they should sooner or later. Yeah, oh, there it comes. Okay, let's see then if I go back now. So that means I put here a thumbs down, because if you have this kind of behavior here in your diagram, you should do something before you start doing the testing. Now let's go to another one, that is how many inputs do we have. As I started out saying, we need to have multiple inputs, because this is actually one of the assumptions. This is what all the methods we are using actually likes to have. There can of course be cases where you cannot get multiple inputs, but if it's possible for you to do something in order to get it, this is what you should aim for. If you look at the singular value decomposition, you will actually see that when you have a single input only, there is only one of these singular value lines that is significantly larger than the others. All the others, they are in some way going down, and there's a lot of dB in the difference between the two. So this is an indication that you have a single input. You can also see this if you are studying earthquake data that has been recorded on a building. Normally that's also a significant shaking of the ground. And many times it looks like this, the kind of singular value diagrams you get. And of course, this is not the most suitable way to make, you could say, a modal testing of the structure, because you need to have multiple inputs. If I have two inputs at the same time, suddenly I can see that the second singular value is also now popping up. That helps me here, because I have my two closely spaced modes here. Now it helps me indicating that there are two here. Up here is a little bit more fuzzy what's going on, because you don't really know what is happening here. So as you add more inputs that are independent, you get actually more and more of these singular values here popping up. We can try, see, we can, I don't know if we can do it, we can try. If I start here, I think if I tap this point here, try that. So I simply go to this point here. Let's see if it will update. You can see now there is a kind of one singular value line coming up here, basically. And yeah, I can try to see if I'm not a drum player in general, but I can try to do two places now. And then you can now see how the two singular values are popping up here. And this way, if I had more hands, I could actually use a third and a fourth and get those to appear also. But this is just a way to indicate or to visualize that we need to have multiple inputs. Because if we're just putting a shaker in a single point, shaking that point with some random noise, it will not really give us the amount of required information that we need in order to really separate modes. We need to have input from many locations. Let's go back here. So remember that multiple inputs if it's possible. There is also the cases where you have something that is rotating. So you have a rotating machinery standing on your structure here, and you want to test this structure here, and suddenly you can actually see some strange things in your singular values. These very strong, very narrow peaks here that is originating from whatever is rotating. So this is, you could say, the fundamental rotational speed in frequency that is showing up here as the first peak here. Sometimes there will be additional orders, so there'll be a multiplum of the first one. This is the second one, and we have the fourth one over here also. So this is just a plate where we have had a shaker standing here in a single point, and then we have been tapping at the same time on this structure here. This gives this kind of signal here, or result to look at. One thing that you can see when you want to detect if this is a mode or if it's a harmonic, that is actually to go to the lower singular values. If they all seem to have a kind of a spike, you can see there's spikes here in all these lower singular values, and all up here also. You can actually also see it here. All the red and the blue and the green, they all have a spike like this. This is an indication that this is a harmonic excitation. It's not a mode that is really, really low damped. Because when you have something that is, say, externally exciting your structure at a certain frequency, all modes at that particular frequency is being excited. And that's indicated by the spikes in all these singular values here. So that's the way that you can immediately see if this is a mode or it is a harmonic peak. But again, you can only do it if you have multiple lines to look at. That means you have to have multiple channels, and you also need to have some kind of multiple inputs. If you only have a singular value line, the first one here, then you have to make up your mind based on that one. If this is your peak of the mode, or is it a harmonic, or what is it, and what is this? Is that the mode, or what is that? But having several lines, it allows you to see the spike all the way through here, and that allows you to conclude that this is the harmonic, and the other one is the mode. So this is a harmonic peaks from sinusoidal excitation, how that looks in a diagram like this. And again, you could say during your test phase, it's really good to know if you start looking at your singular value diagram, maybe you will have something at 50 or 60 hertz, depending where you are in the world. If you have a large spike there at this frequency here, it might be something related to the electricity, the grounding, or something else. So again, check the equipment if it's not because you have an engine running on your structure, of course. So the last thing that I also like to emphasize when we look at the singular value diagram, that is actually if you have a channel that in some way becomes bad. I have actually, to create this diagram here, I was using this connector here yesterday, and then just having it sitting on top of it without having it really attached properly. So suddenly you had a bad connection in this case here. When you then start doing the testing and seeing the singular value diagram appearing, you will see something like this. So normally you will see that most of the diagrams look really nice. I mean, very nice modes, but there is something strange going on like this thing here. So this is simply because you have one or more channels that are bad in some way, bad channels. That is a loose sensor, for example. It's a broken cable. Maybe the sensor dropped off while you were doing the test. It happens to everyone. If you're using wax or something, you're not gluing the sensors, you can easily have a sensor that drops off. And that will then appear something like this. There will be something in the diagram that's not supposed to be there, like in this case here. So again, it's a very convenient place to have this single diagram that allows you to see this immediately. Okay, so let's try now to go back to the software just to finish the test. So what I'll do now is I'm at setup number 1 here. I will now start the recording here again. And now I will start like this. So what's happening now is you can see down here is waiting for triggers. So now it's awaiting me to start exciting with multiple inputs the structure, and then after that it will then start the recording, and then we will see that it will last for 60 seconds in this case here, and you can see now I'm simply spreading out this excitation completely random across the whole plate here to in this way simulate multiple inputs. This is the best way you can get some very good results, and you can see all the singular values. They seem to be alive, indicating that you actually have these multiple inputs available. And as we increase the measurement time here, the average of this diagram here becomes better and better, and we can see that the scatter that we have in the different lines is reduced. And hopefully in the end it will be nearly invisible. So we are nearly there for the first measurement here. Now she tells us that it's complete. And now I can switch to the next setup here. like this. And of course, I also need to remember to move the sensors here. So I will simply take them one by one here. Move them to the second setup. This. This. And then we try again. So now we are at setup number 2 up here. And we start the recording. And we are waiting now that I start tapping. And now it's triggered. Then we are finished now, and we can now jump to just to check the data. We can do that in the Manage Measurement task here. And here we can then check out the different channels. This is the first setup that has been selected here. We can also select setup number 2. And we can check out, and it looks fairly good. There is no outliers or dead time or anything. So this looks to be promising. Let's see then, I can now go and start doing the actual mode analysis then. I'll do a little short. We have shown that several times before. But it basically starts in this analysis prepare data task here. Here we configure the actual analysis we want to do. What do we want to do with the raw data? Here we can choose decimation and filtering and detrending. We can also choose here how to set up the spectral density estimation. And then down here in the end, we can configure the so-called Stochastic Subspace Identification methods in the case we have the pro version of the software. And I try to use the method called UPCX here. That is a method that allows us to give low parameters as well as their uncertainties. I simply start the processing here of the raw data first, and then spectral densities, and then the preparation for the stochastic subspace identification methods happens after that. This is what is going on right now. And then once this is completed, then automatically it will estimate the modes using the SSI method that has been selected. This is because we choose to use automatic SSI estimation here. That means that when we now go to the estimation task to actually see the stabilization diagram, we actually basically have just to inspect everything is okay and perhaps do minor modifications. Most of the work should have been done for us by that time. So you can see now that the automatic estimation is happening. This is done per setup. So now we have 2 setups. So you would say we have to do the estimation of the modes and the uncertainties 2 times. And then in the end, we can merge the things together. And a list of all the modes are then popping up here. You can see here that in the estimation task here, we have the UPCX method here selected, showing us the modes. We can try to animate, see if we are lucky. It looks like we had some successful measurement made. So we get some nice modes here, like this. And of course, we can now, you could say, double check it by choosing another method. We can, for example, go to the simple FDD method. And then we can try to use the peak picking method to pick out the same modes, so we have something to validate up against. And if I do that, if I choose to click this little button here, then I have this little cross that is sticking to the peaks of the different modes where they have resonance. And the first one here, I simply double click when I'm at that point, and then I get the mode shape immediately estimated here, as you can see. And then we can do exactly the same operation for some of the others here, like this. If we go to this one here, we probably need to zoom in a little bit just to see what's going on here. You can see that we have one probably here, and then another one like this. So in this way here, we can zoom in on the cases that are a little bit more difficult. And then it's very easy and convenient that you have this zoom facility here, so you can easily zoom a segment like this through. So now we can go to the top part here and then take out this also, like this. This one is a little bit poor, it seems, but anyway, it's like it is. So we have modes here from the FDD methods, and we have modes from the SSI analysis we had before here. In this case here, we can now do some validation. We can try to compare the things to one another. So if I select validation here, I get the list of modes that I have. This is the FDD modes. And down here I have the SSI modes. One thing that you should note is that we have the frequency, but we also have the standard deviation of the frequency here. We have the damping ratio and the standard deviation here. This is not available in the FDD methods. This is a very simple method of here. But we can choose, for example, the first mode here, and then choose to overlay the animation of the same mode from another estimator. So we now compare the first mode of FDD with SSI, and then see how this looks. And you can see how things are moving here. The red one here is the SSI mode, and the blue one is the mode shape of the FDD mode. And this way you can actually continue. You can actually use this. You can go here and you can double click on this one here where they also compare quite good. And here you can actually see then the two mode shapes being compared in this diagram here. We have here the two selected ones here showing up in the table here. One can also subtract the two animations here. So instead of looking at the actual amplitudes together here, you can try to subtract the two mode shapes and then animate the difference instead. This can be done by selecting this button here. And suddenly we can see, for example, that a node up there is moving a little bit. So in this way you can pinpoint where you have the largest errors in your data. This is some of the things you can do for validation in the software. Now I promised only to use 1 hour. So let's go to a little conclusion here now. Just to conclude that ARTeMIS is a very open platform. We have the ability to actually also communicate directly with different types of data acquisition hardware. For now, it's only the 4 that you see listed here: National Instruments, Sinus Mesh Technique, HDL Dynamics, and HBM from Germany. This is what we have right now, but there will be more coming up later on. You can also upload data directly from files. So if you have measurement files, you don't have this hardware available, but you have things stored in a measurement file, you can actually upload it also directly. And we have more than 20 different formats that we support currently. We use both single and multi-setup. What you saw today was a multi-setup modal estimation, but you can also, of course, use just a single setup if you only have a single measurement on the structure. That's very used when we do things in structural health monitoring, when we are measuring with permanent instrumentation on a structure. We have other plugins available for other things like the classical experimental modal analysis and all kinds of plugins for structural health monitoring also that I have not shown today. For the operational modal analysis, you can say we have up to 8 different techniques that works in parallel, so you can use 8 different ways to estimate the modes and then make a validation, a comparison between the different estimators. We have both frequency and time domain methods available. Some of them actually provide uncertainty information, as I've shown today, of the mode parameters also. And then there are several different validation features available. And finally, there is some more information that you can get if you go to our YouTube channel. This is a little bit, this is the way YouTube shows it. When you copy the link, it's not very user-friendly. But if you go to YouTube and you search for ARTeMIS Modal, then you will find this channel here, I'm sure. We also have our website where there's a lot of literature, and you can actually download software for testing. You can try it out for 30 days if you want. Next time we have a webinar will be on January 20, and we will be talking about structural health monitoring using ARTeMIS Modal. So I wish you all good health and a good day. Thank you very much.